Doc Edgerton inspired us with awe and curiosity with this photo of a bullet piercing through an apple, an exposure just a millionth of a second. But now, 50 years later, we can go 1,000,000 times faster and see the world not at 1,000,000 or 1,000,000,000, but 1,000,000,000,000 frames per second. I present to you a new type of photography, femto-photography, a new imaging technique so fast that you can create slow motion videos of light in motion. And with that, we can create cameras that can look around corners beyond line of sight or see inside our body without an X-ray, and really challenge what we mean by a camera. Now, if I take a laser pointer and turn it on and off in 1/1,000,000th of a second, which is several femtoseconds, I'll create a packet of photons barely a millimeter wide. And that packet of photons, that bullet, will travel at a speed of light, and again, 1,000,000 times faster than an ordinary bullet. Now, if you take that bullet and take this packet of photons and fire into this bottle, how will those photons shatter into this bottle? How does light look in slow motion? Now, the whole event now remember, the whole event is effectively taking place in less than a nanosecond. That's how much time it takes for light to travel. But I'm slowing down in this video by a factor of 10 billion so you can see the light in motion. But Coca-Cola did not sponsor this research. Now, there's a lot going on in this movie, so let me break this down and show you what's going on. So the pulse enters the bottle, our bullet, with a packet of photons. They start traveling through, and they start scattering inside. Some of the light leaks, goes on the table, and you start seeing these ripples of waves. Many of the photons eventually reach the cap, and then they explode in various directions. As you can see, there is a bubble of air and it's bouncing around inside. Meanwhile, the ripples are traveling on the table. And because of the reflections at the top, you'll see at the back of the bottle, after several frames, the reflections are focused. Now, if you take an ordinary bullet and let it go the same distance and slow down the video, again by a factor of 10 billion, do you know how long you'll have to sit here to watch that movie? A day, a week, actually a whole year. It'll be a very boring movie of a slow, ordinary bullet in motion. And what about some still life photography? You can watch the ripples again washing over the table, the tomato, and the wall in the back. It's like throwing a stone in a pond of water. By the way, this is how nature paints a photo, one femto frame at a time. But of course, our eye sees an integral composite. But if you look at this tomato one more time, you will notice as the light washes over the tomato, it continues to glow. It doesn't become dark. Why is that? Because the tomato is actually ripe, and the light is bouncing around inside the tomato, and it comes out after several trillionths of a second. So in the future, when this femto camera is in your camera phone, You might be able to go to a supermarket and check if the fruit is ripe without actually touching it. So how did my team at MIT create this camera? Now, as photographers, you know, if you take a short exposure photo, you get very little light. But we're going to go 1 billion times faster than your shortest exposure. So you're going to get hardly any light. So what we do is we send that bullet, those packet of photons, millions of times and record again and again with very clever synchronization. And from the gigabytes of data, we computationally weave together to create those femto videos I showed you. And we can take all that raw data and treat it in very interesting ways. So Superman can fly. Some other heroes can become invisible. But what about a new power for a future superhero? To see around corners. The idea is that we're going to shine some light on the door. It's going to bounce, go inside the room. Some of that are going to reflect back on the door and then back to the camera. And we're going to exploit this multiple bounces of light. And it's not science fiction. We have actually built it. On the left, you see our femto camera. There's a mannequin hidden behind a wall, and we're going to bounce light off the door. So after our paper was published in Nature Communication, it was highlighted by nature.com, and they created this animation. We're going to fire those bullets of light, and they're going to hit this wall. And because of the packet of the photons, they will scatter in all the directions, and some of them will reach our hidden mannequin, which in turn will again scatter that light. And again, in turn, the door will reflect some of that scattered light. And a tiny fraction of the photons will actually come back to the camera, but most interestingly, they will all arrive at a slightly different time slot. And because we have a camera that can run so fast, our femto camera, it has some unique abilities. It has very good time resolution, and it can look at the world at the speed of light. And this way we know the distances, of course, to the door, but also to the hidden objects, but we don't know which point corresponds to which distance. By shining one laser, we can record one raw photo, which you look on the screen doesn't really make any sense. But then we're going to take a lot of such pictures, dozens of such pictures, put them together, and try to analyze the multiple bounces of light. And from that, can we see the hidden object? Can we see it in full 3D? So this is our reconstruction. Now we have some ways to go before we take this outside the lab on the road, but in the future, we could create cars that avoid collision with what's around the bend. Or we can look for survivors in hazardous conditions by looking at light reflected through open windows. Or we can build endoscopes that can see deep inside the body around occluders, and also for cardioscopes. But of course, because of tissue and blood, this is quite challenging. So this is really a call for scientists to start thinking about femto-photography as really a new imaging modality to solve next generation of health imaging problems. Now, like Doc Edgerton, a scientist himself, science became art, an art of ultra-fast photography. And I realized that all the gigabytes of data that we're collecting every time is not just for scientific imaging, but we can also do a new form of computational photography with time-lapse and color coding. And when you look at those ripples, remember, the time between each of those ripples is only a few trillionth of a second. But there's also something funny going on here. When you look at the ripples under the cap, the ripples are moving away from us. The ripple should be moving towards us. What's going on here? It turns out, because we're recording nearly at the speed of light, we have strange effects. And Einstein would have loved to see this picture. The order at which events take place in the world appear in the camera with sometimes reversed order. So by applying the corresponding space and time warp, we can correct for this distortion. So whether it's for photography around corners, or creating next generation of health imaging, or creating new visualizations, since our invention, we have open sourced all the data and details on our website. And our hope is that the DIY, the creative, and the research community will show us that we should stop obsessing about the megapixels in cameras and start focusing on the next dimension in imaging. It's about time. Thank you.